Hello. Today we're going to be talking about the end of this chapter and we're going to talk about electric potential. So what is electric potential energy? So what that is energy that a charged particle has due to its location in an electric field. And I want to stop right there and develop this comparison. So we already learned about this term potential energy. We've talked about that before in this course. And you heard me say gravitational potential energy. So we talked about taking something with mass and lifting it to a higher location, and it then had potential energy. And we learned that the formula to calculate its potential energy was mass times the acceleration due to gravity, or m times g, its weight, times its height in that gravitational field that it's in. So mgh, or the weight times the height. And that's how we talk about the gravitational potential energy. Electric potential energy, we can start to think of the same way. It's a potential energy that a charged particle has due to its location, not in a gravitational field, but in an electric field. So I have this little charged particle. It's positively charged. You probably can't see there's a negative sign in this bigger one down here. So this is a negatively charged body. It's got an electric field that's associated with. I know that this positively charged thing, this little charge here, wants to move close to that negatively charged object. That's the direction of this electric field. That's the direction this positively charged particle would move, toward the charged body, right? So if I take and I move it away from that charged body, I've given it potential energy. So if I suddenly stop whatever support is holding it there away from that negatively charged body, it is going to begin to accelerate toward that negatively charged thing. So it has potential energy. I release the thing that's holding it and it obeys the laws of physics and it moves. You know that as it moves, it's losing potential energy. The further it is away from this thing, the more distance it wants to be able to cover to get next to it, right? So as it accelerates toward this charged body, it's losing that potential energy and it's trading it for kinetic energy. So if I have this charged body that's positively charged and this larger negatively charged body that is generating this electric field here, I know that I need to actually do something to move it against the field. Just like my massive thing, I had to do work to move it against the field. I had to do work to take this massive thing and lift it to a higher height. If this positive little positive charge was stuck to this negatively charged body, I would have to do work to separate them and move this against the electric field. All right, you can also think of it like this. This spring in this illustration has more potential energy when I push it closed, when it's compressed. The charged particle has more electric potential energy when pushed closer to the charged sphere. In this case, the charged sphere is positively charged, and my little thing that I'm looking at is a little positive charge. So I would have to do work, just like pushing the spring, I would have to do work to bring those two close together. I would have to work against the field. So remember, unlike gravity, these electric fields can be either attractive or repulsive. Gravity is just attractive. So if we're looking at this spring and we're looking at this little charge that I'm putting some work into, I have to do a force to move it against the field. I have to generate a force. In both cases, that increased potential energy is going to be because I put work in. Okay, so a lot of times when we're talking about electric potential, we use this term voltage. What is voltage? How are we going to define that? It's the energy per charge that a charged particle has due to its location. So a charged particle might be 1 coulomb, it might be 2 coulombs, it might be half a coulomb. So for example, an electron is a really small fraction of a coulomb. So the electric potential is the energy per charge that a charged particle has due to its location in an electric field. We call it voltage. It's the potential energy per charge. Here it is in equation form. The electric potential is equal to the electric potential energy divided by the amount of charge. So if we go back and we're looking at this illustration, I'm talking about however much charge this little thing has. This is the thing generating the electric field, okay? So I am talking about how many coulombs this little guy is, and I'm talking about the energy that it has per units of whatever charge the smaller one has here. So when we look at our units of measurement, 1 volt is equal to 1 joule divided by 1 coulomb. So if I take a 1 coulomb charge and I do 1 joule of work to it, I have given it the potential energy, the potential of 1 volt. Okay? Twice the charge in the same location will have twice that potential energy, but the same electric potential, because this is electric potential. So if I have a 2 coulomb charge, well then to get it to the same place, I'm going to have to do 2 joules of work to it. So that's going to be 2 joules divided by 2 coulombs, which is still going to be 1 volt. So if we continue to use this same logic here, 3 times the charge in the same location will have 3 times the potential energy, but the same electric potential. So if it were 3 coulombs, I would have to do 3 joules of work to it to get it into the same place, but it would be 3 joules divided by 3 coulombs and still 1 volt. So let's check a little bit for understanding here, one of our multiple choice questions. Electric potential energy is measured in joules. Electric potential, on the other hand, which is electric potential energy per charge, is measured in what? Volts, watts, amperes, or also in joules. I'm going to give you just a second to think about it. Not too hard. It's what we've just been talking about. It's measured in volts. We don't really need to talk about that. This you should know. Electric energy storage. Electric energy can be stored in a device called a capacitor. So this is a component that's part of a lot of your electronic devices that you have at home that you use. If anybody still, I know that they're in cameras, say, because I need to use a lot of energy all at once if I want my camera to provide a flash. I know that they are in cameras, and I know that they store energy because one time when I was a child, I had a camera and it broke, and I needed to hide this from my parents because I was afraid I was going to be in trouble. And I took it apart. I stayed up at night. I took it apart after everybody had gone to bed. It was probably like 8 or 9. And I'm poking around in the innards of this camera, and I touched some little piece of it that ended up being this, that ended up being a capacitor inside the camera, and it gave me a zap for sure. So what a capacitor does is it stores energy. So the simplest one we can think of that we use to start to describe this is just a pair of conducting plates separated by a small distance, but they are not touching each other. We then connect those plates to a charging device, such as a battery. You know, a battery has a positive terminal and a negative terminal. So electrons are then transferred from one plate to the other. So this plate is going to get an excess of electrons. This plate is going to lose electrons. This plate gets an excess of electrons. And now there's an electric field between them, and I am storing energy. So those capacitor plates then have equal and opposite charges. The positive plate is connected to the positive battery terminal. The negative plate is connected to the negative terminal. The charging process is complete when the potential difference between the plates is the same as the potential difference between the battery terminals, which is the battery voltage. So the greater the battery voltage and the larger and closer the plates, the greater the charge that we can store in that capacitor. The energy comes from the work that's required to charge it. It says here, discharging a charged capacitor can be a shocking experience if you happen to be the conducting path. So that was me with the camera, and I would encourage you not to take apart any of your electric devices and try to fix them yourself unless you actually know what you are doing. And here, a while ago, I told you I would briefly explain how that Van de Graaff generator works. So this is a simple diagram of the inside of a Van de Graaff generator. So this is the dome. Remember the woman with the long hair that I said was Paul Hewitt's wife? Her name is Lily, and she was touching it, and she was building up electrons on her outer surface. This is the Van de Graaff generator. This is like the thing that she had her hand on. So inside, when I plug the thing in and I turn it on, and what happens is it makes this belt go. Okay, so this belt is going around like this, and it's rubber, and as it goes around, it goes past these metal points. So there's something kind of like a brush or a fork looking thing. It has a lot of little spikes, and they're made of metal. So it goes and it picks up some electrons from this metal brush. So it takes them up here, it's going around, and here is another metal brush. So the electrons jump off and they get onto that, and then they go out onto the surface of this sphere that is the surface of the Van de Graaff generator. This is important. The electric field inside that sphere is always zero. So the charges that go off the belt onto the collector and out into the sphere are not repelled by charge stored on the outside of the sphere. So in here, the electric field is always zero. And that's how the Van de Graaff generator works. Okay, so the really important things that we talked about to sum up this little section here, you learned that we call voltage electric potential, or we call electric potential voltage. And you know, when you go to the hardware store or wherever you buy a battery, you look at what voltage that battery is. That is equal to the electric potential energy, which is given in joules, divided by the amount of charge, which is given in coulombs. So this is in joules. Try to write this for you. And then the amount of charge is in coulombs. So when I talk about voltage, I am talking about joules per coulomb. And we also briefly talked about the electric field everywhere inside a hollow conducting body is zero. You should remember that as well. But for sure, you're going to need to know this.